Okay, good morning, everybody, and welcome to the final event of the NewWave project, when we will disclose some results about the activities of the project, in particular, as you see from the title, wood products, green resins, and chemicals. I'm Giulio Poggiaroni, also from ETA Florence, one of the partners of the project, and I will help making this session smoother across the various presentations and the speakers we might have. We have many people connected online, so as you can see from the program, there will be a few sessions, and then there is an open discussion/Q&A part at the end. So if you have questions, be sure to put them in the chat. We will collect them and we will answer at the end. We recommend you to put the question right after the speaker of your interest has spoken, so that you don't forget the questions. And for those in the room, there will be them. We will pass the microphone, so don't forget your questions. So time for the first speaker. Actually, the coordinator of the project, Bert van der Belt from Biomass Technology Group, who will provide us a short welcome and keynote about the project and the core technology of NewWave, the thermochemical fractionation. So, Bert, the floor is yours.
Yeah. Good morning. Also, welcome to this final event at a lovely location here in Isola in Slovenia. It's a very good place to be. What I will do is briefly introduce the NewWave project. It's just one slide, and then go to the core or the basis technology we use in this project, and that's the unlocking the biomass via fast pyrolysis. So this project, the overall objective of NewWave, a project which started about 4 years ago, it's the transformation of existing fossil-based manufacturing lines, and we want to change it into a bio-based manufacturing line. One target is to have at least the same products or the same quality of products, or even better products if possible. And one aspect is also preferably it's non-toxic and recyclable. So that's all within the project. At the bottom, you also see the beneficiaries, the project partners of this project. So the starting point of NewWave is to unlock the biomass, to have the different functionalities of biomass available for further processing. It's a two-step process. We call it thermochemical fractionation, TCF. It's a two-step, and we try to convert biomass in new raw materials. The first step is this fast pyrolysis, and we convert sustainable biomass into a liquid, the liquid called FPBO, the liquid product. Basically, it's liquid biomass. And the second step is to start with this liquid and then fractionate it into different fractions. And each of these fractions can be used as a raw material or for further process. And that's actually what we do as a starting point. The first step is fast pyrolysis, probably quite well known. It's just an overview here. Fast pyrolysis is the thermal depolymerization of organic material with no oxygen or very low oxygen. We really aim at making a liquid, so we try to maximize the liquid product. We think the conditions are quite mild. It's temperature of around 500 degrees C, it's atmospheric pressure. And this process has been developed in the last decades and is commercially available. Some plants have been built in Europe. There is one in the Netherlands, in Sweden, Finland. They all have a standard capacity of around 5 tons of dry biomass an hour, which is roughly 25 megawatt. And these plants can be delivered as turnkey units. So that's the first point. The production of fast pyrolysis, it's available. It's commercially available. You can just order a plant. Then the second step is how to get the right fractions for chemicals and materials. And that's what we call the FPBO, the fractionation into the useful fractions. It's important to realize that in fast pyrolysis, the key functionalities are still in the pyrolysis oil. The key functionalities of the biomass are retained in the pyrolysis oil. And what we do, it's a separation on basis of liquid extraction. Basically, it's a separation on basis of functionality, and that's important. The other way is to do it on boiling point, but then you won't get a separation where you really separate the functionalities. Well, each fraction can be used directly in bio-based products. That's also what we have done in this project in NewWave, or we try to further convert it to new chemicals materials. What you see in the scheme is basically the overall. We start with biomass. Biomass consists of typically hemicellulose, cellulose, lignin, extractives. In pyrolysis, you depolymerize it, you get a smaller fraction of it, but still contains a lot of these functionalities. We see the acids, ketones, aldehydes. Cellulose typically leads to the carbohydrates or the sugars. Lignin, what we then call the pyrolytic lignin, it's different. It's smaller size, lower molecular weight. And all these products in the pyrolysis liquid are free of minerals. There are no minerals, acids, ashes in the products. In the fractionation, so then we start with the liquid and we just try to separate it. We get an acid fraction, a sugar fraction, lignite fraction, and you can have some extractives. Extractives are something like the tall oil, the resins, the fatty acids. The main activity within NewWave is concentrate on using the pyrolytic sugars and the pyrolytic lignin. How does this process look like? It's a schematic drawing here. We have two liquid extraction. In the first step, we can remove extractors, but it's commonly not done. Very often it's not needed. So very often the first step is skipped. Then normally what we do, and that's also what we did here in this project, is start with fast pyrolysis or have an liquid extraction with an aqueous extractant, water. We get a separation between sugars and lignin. What's mentioned here is the liquid pyrolytic lignin. That's the first product. But in many cases, the solid version is preferred. So there is an additional step where we convert the liquid pyrolytic lignin into the solid one, and that's also one of the products we used in NewWave for further development. In that case, we also get light phenolics. So this is the overall process. For this process, we also built a pilot plant. We have the demo plant running at BTG. It's typically the capacity is around 120 kilogram an hour. So 3 tons a day can be processed in this plant. Either we do the aqueous extraction or the organic extraction, but as mentioned, normally we do the aqueous one. We get the lignin and the sugars. Also for this process, there is a REACH registration, this CAS registration. You can all find them. On the left-hand side, it's the pilot plant at BTG. Well, it's proven on small scale. So if you look at the status of this fractionation step, of course, it's important to have the first step proven before you can develop further products from it. It is proven on a pilot scale of 120 kilogram an hour, as mentioned. BTG has a technology license with BTG Bioliquids. It's our sister company for implementing the technology. So to go to the further step from pilot scale from the lab to full-scale demonstration. The full-scale demonstration will be roughly 1 ton an hour of pyrolysis oil. The design has been completed. It should produce around 1,500 ton of solid pyrolytic lignin a year. Likely it will be used in insulation material. This first demonstration is not done by us. It's foreseen 26, 27. I think it will be early next year, or hopefully it will be early next year. It will be done by a company called Aurora Renewable Chemicals, and they want to extend an existing pyrolysis plant, and Pyro in the Netherlands. They will add a fractionation plant to it to be able to produce larger quantities of these fractions. So what are we doing in NewWave? It's here you see the TCF conversion plant. That's the basis. From there we make the different products, lignin, sugars, and we also still have the pyrolysis oil itself. And we have defined the different manufacturing lines. And with the manufacturing line 1, it's for engineered wood panels. There's one on HMF and furan-based chemicals, polyols, and the ethylene glycol, propylene glycol, and polyurethane. It's one, and we have one for modified wood to improve the durability of wood. So these are the 4 manufacturing lines which are further developed within NewWave from the different fractions. The TCF, of course, starts with all kinds of biomass residues. It should be sustainable. There is also something on circularity in the project, because the products from a particular manufacturing line 4 and 1, it's about these wood panels and the modified wood. At the end of life, they can be reused in the pyrolysis plant to produce again the pyrolysis oil and do the whole value chain again. So there's the circularity. Another aspect which is further developed in the project is about the wastewater, because as said, this fractionation is partly based on aqueous or water extraction. It means there is a recycle of water. There might be some organics there, so there is a wastewater treatment. And we produce some biogas that can be used within the process. It's cleaning the water, but we can also reuse the water in the fractionation. So this is the whole NewWave project, with a focus on the 4 manufacturing lines. And that's actually the next 4 presentation is describing, each of them is describing one of the manufacturing lines and the results and the progress on these manufacturing lines within the NewWave. And actually we can see some of the products here on site. It's a pity if you're not on site, you cannot see them, but we will visit the demo materials. So that's all as an introduction. I think we will then continue with presentations on the different manufacturing lines. Right. Thank you.
Thank you, Bert. So now we move into the technical manufacturing lines of the NewWave project. And we have the first intervention from Foresa Technology, which is the Spanish partner involved in this, and they are intervening from online. So I would like to ask, probably Sandra is connected. Sandra, can you hear us?
Yes, and you?
Yes,
everyone?
Loud and clear.
Okay, thank you.
You can proceed.
Yeah, so good morning, everyone. Today we present the work done by Foresa Technologies as part of a NewWave project. Our focus has been on pushing the boundaries of sustainable chemistry through good products, green resins, and innovative bio-based chemicals. Next slide. Thank you. To understand our role, it helps to see where we come from. Chemistry has been the foundation of our company, Foresa. And since it was founded in 1964, since then, we have grown over the years. Currently, Foresa facilities are strategically distributed across Spain, France, and Portugal to guarantee the fast service and efficient technical assistance to our customers. Here in Spain is the heart of Foresa's operations. This site is home to our main offices, our production lines, and our technical hub, the Foresa Technologies. That this is a spin-off of Foresa, which brings together innovation, sustainability, and industrial property. Next slide. Thank you. To give you a better idea of who we are, let's look at our background and how our chemical expertise has evolved. This diagram shows the direct flow from our raw material to the final industrial applications. If you look at the blue column on the left, this is our foundation, raw chemistry. We work with essential components like methanol, urea, and melamine, but also, and crucial for this project, with natural raw materials and additives. We then transform those materials into our core resin technology. And beyond our traditional formaldehyde and phenol concentrates, we have diverse into environmental solutions like AdBlue for noise scavenging, among others. And most importantly, we are pushing into BioLine, developing the bioemulsions and bioadhesives that represent the future of our industry. So our technology serves a wide range of sectors, while wood panels, papers, and construction remain our primary markets. And our technology now reaches sectors as diverse soil erosion control, and even high-end furniture and decoration. In short, this reflects what Foresa is all about, using chemistry as a tool to provide cross-sector solutions, moving from traditional methods toward a more sustainable future. Next slide. Thank you. Now, moving on to our naturally originated solutions, our main objective is clear. We want to replace fossil-based raw material with renewable natural resources. As you can see, we have two primary lines of development. On the left, we focus on waste from the agroforestry sector. From this biomass, we have created Lignature, a biomass-based resin, and Pinature, our vegetable origin resin. On the right, we explore solutions derived from vegetables, proteins, fats, and sugars. This has led to development of Forsoy, which is a protein-based resin, and Biowash, a high-performance water-repellent emulsion made from vegetable fats. These products represent our commitment to a circular and sustainable chemistry industry. Next slide. After that, turning to NewWave project, Foresa leads work package 5. Next slide. Yeah, thank you. Our main goal here is the design and upscaling of added value green resins, specifically based on pyrolytic lignin. We are not just looking for a laboratory success. Our goal is develop the fully sustainable MDF and plywood products that can be produced in a large quantity for real-world demonstrations. As you can see from the timeline, this is a comprehensive 4 years effort. We move from initial resin development and sample manufacturing in the first and 2 years to intensive life cycle analysis and industrial conversion in years 3 and 4. And everything culminates in our final milestone. The success. I hear echo. Yeah. So our final milestone, the successful production of 100% bio-based resin. Next slide. Thank you. So our technical approach involves a direct comparison between a standard resin and our bio-based alternatives. In our phenol replacement strategy, we substitute traditional phenol with pyrolytic lignin. We aim to maintain the polymer's structural integrity while significantly decreasing or reducing the fossil fuels. Next slide. In our pilot plant, we successfully manufactured plywood panels using a resin where 50% of phenol was replaced by solid lignin, called SPL3. The results were quite good because the panels successfully meet both Class 1 and Class 2 treatments for the standards, as you can see in the table. This was the best resin obtained with the optation for the plywood panels. Next slide. So, as the same way, we elaborate MDF resin, in this case with 25% of lignin. With this resin, we are able to elaborate MDF panels that reach with the standard. If we increase the percentage of the lignin into these resins, both plywood or MDF, the panels that we obtain not reach with the standards. That's why these two kind of panels was the elaboration for the demonstration for this NewWave project. Next slide. Try to develop a complete green resin. Both phenol and formaldehyde should be a replacement for for that. The candidates are the lignin, cresol, and hydroxymethyl furfuryl, respectively. Next slide. So for phenol replacement, the project started with 4 different pyrolytic lignins. However, in the middle of the project, a combination of 2 of them, called SPL3 lignin, result that was the best lignin to continue with the project because we obtained the best results. On the other hand, also blended phenols or cresol was also tried, and both of these samples was provided by BTG company, like he said before. Next slide. In the case of formaldehyde replacement, the project started with HMF commercial one and was compared with 2 more samples provided by transfural chemicals. One of the HMF sample was 50% concentration, and another one was a solid with a purity of 99. On the other hand, also was tried DFF as alternative of HMF, although it was not initially contemplated in the project scope. And this raw material, the DFF, was also provided by BTG. Next slide. In the case of the development of a green resin with cresol and HMF, we only modified the pH starting in the standard recipe. The rest of the parameters, as temperature, was not modified. Despite we obtained the final resin, the gel time, as you can see, was higher enough to say that this resin doesn't cure, has no reactivity. This can be proved with the rheometer. As you can see, there is no significant curing peak, and the modulus remains near 0 through the temperature. Moreover, the DSC is possible to observe that the degree of curing or cross-linking is far lower than the standard resin. And even the GPC shows shorter polymer chains as the cresol samples. That means that less extensive polymerization compared with the standard resin. So next slide. So therefore, we switched the cresol for pyrolytic lignin, maintaining the HMF to elaborate the 100% bioresin. In this case, we should modify the standard recipe, not only increase the pH at the beginning of the reaction to avoid precipitation formation, but also the temperature. The temperature had to be drastically elevated, around 95 degrees, for the polymerization stage. Implementing this modification allows us to achieve a viscosity similar to the reference. However, the high held time, around 130 minutes compared with 19 minutes of the reference, indicates that the resin process low reactivity. This can be observed in the rheometer analysis, where the modulus is near 0, and the DSC also show a lower enthalpy, indicating difference in and less efficient polymerization. The GPC also show lower molecular weight compared with the reference. Next slide. So in view of the harsh condition required to elaborate a 100% bioresin, the use of DFF has been proposed as alternative to HMF. Although, as I said before, it was not initially contemplated in the project scope. Trials with DFF reveal significant technical issues. The solid nature of DFF requires a temperature near 99 degrees for dissolution, which is industrially impractical. Moreover, during the polymerization process, precipitation was observed and could not be removed, as you can see in the pictures. Therefore, the elaboration of this resin, the resin, could not be continued and was not possible to obtain this resin. But however, since we select a specific recipe without any modification, A more in-depth study could be performed in future projects to optimize these production conditions. Because as I said, this was not initially contemplated and we don't have time to change it, making good conditions for this kind of resin. Next slide. Thank you. Therefore, with the green resin obtained but with lower reactivity, the 100% lignin and 100% HMF, we performed particle board panels with good chips provided by Foreco, and these good chips were maple and radiata pine. The first trials resulting panels were difficult to handle due to the structural failure. This was because the low density and morphology of the specific good chips used. So to improve these particle boards, we increased the percentage of the resin and the curing time to elaborate these panels. So these adjustments provide that the good chips were fully coated with the resin, and it compensates the low reactivity of the resin and these technical limitations. The characterization was carried out, but unfortunately, the panels did not reach with the standard value, as you can see in the table, in the internal bond table. Next slide. So as a conclusion, we elaborate high scaling plywood and MDF panels with the replaces of 50% and 25% lignin, respectively, because these conditions were the ones that the panels achieved with the standard. The issue is that this resin is not 100% bio-based, and the free formaldehyde content obtained is too high. And therefore, the goal was elaborate 100% bio-based resin. We tried the Cresol HMF, lignin HMF, and lignin DFF. That was not initially contemplated, and due to the generation of precipitation during the process, the resin could not be produced. In the case of the Cresol and HMF, the resin reactivity was almost null, so there is unsuitable for the panel production. And therefore, the resin with lignin HMF, despite the harsh condition need to elaborate it, make it unsuitable for the industrial process, was selected to elaborate a fully sustainable panels, because in the laboratory we can obtain this kind of resin. So the 100% bio-based resin we choose it for the elaboration of the good chips panels. For elaborated, we have to increase, as I said, the resin content and the press cycle to elaborate the panels, and despite the low density of the chips. However, the panels doesn't reach with the standard. But nevertheless, these represent a successful proof of concept due to the results show that it's technically possible to elaborate panels with 0% formaldehyde and 0% fossil phenol. Yeah, next slide. Thank you so much for being here.
Thank you, Sandra. Okay, now we move to the next part of the presentation, which will be delivered by InnoRenew, the next intervention about modified wood products.
Yes, so I will be presenting this on behalf of InnoRenew, but if Lex is joining us online, so there will be a few slides when he will be showing like how this really looks from the industrial perspective, which is very important here. We were just partner who was characterizing the modified wood and making some recommendation which is performing the best, but the hard work was done by our industrial partner. Okay, we might wonder why biomaterials, and I think here we have all fans of renewable materials here in the room and also online. And I think wood is very versatile materials which allow to create very modern and also very traditional structure. And then one of the famous architects was saying then 18th century was about the brick, and then we had the steel age, concrete, and 21st century is coming back to the wood, even if this was one of the first building materials which was used by the humans. And then when we just think about the wood diversity, there is over 60,000 of different wood species which might be used for different applications. And you might be wondering why we are still needed to improve them. And in fact, when wood is exposed to external factors, is facing several different processes. So we have the weathering, we have decay, waterlogging, action of insects, and so on. And you can see here many things are happening with the wood, with the native structure of wood. Therefore, we have to provide some treatment, especially when we consider wood in the application for the building sector. And then here the wood modification processes are coming in, and they are like classified to two different groups. So there are active modification, where we are using some chemicals which are bounded to the wood cells and improving the properties, or we can have also passive modification, and this is the case for the impregnation, when we are filling the lumen with some liquids, and then they are reducing the shrinkage swelling, they're improving some properties. And when thinking about wood modification, there is like a really broad group of the processes. Europe is leading the innovation here. And then so we have the chemical processes, thermally modified process, and also a lot of hybrid process which are merging different properties. When we think still about the market size, the thermally modified wood is making the majority of the treatments. Nevertheless, the other processes are still in the development, and some of them are commercialized. During the last wood modification conference, we were discussing what are the trends in the wood modification process. And I think here we have the green process were highlighted, and I think the NewWave is fitting perfectly to this trend, because we are really working on the bio-based solution for improving the wood properties. And then coming to the manufacturing line 4, which was like the one we were responsible for. And I think Bert was really nicely presenting the overview here. It is like a really holistic approach to use these fast pyrolysis oils for different applications. And then here, in our case, we were not really making a lot of improvements of the process as other manufacturing line were using, but we were trying to use the solutions which were like the formulation for the improving of the properties. So this is how it was conducted. But I think this next slide is also showing you where we are in the TRL development. So we were bringing the TRL 4.5 to the TRL 6, which means we wanted to validate and demonstrate that the wood modification obtained by the NewWave project is possible to apply in the real condition. And then we had these 3 objectives. So the first was to optimize the formulation, and that was done by our partner BTG. Then we had the big screening phase for characterizing different properties, and based on that, we were selecting the best solution, and then we were demonstrating the technical feasibility to apply those modification process in the real condition. And here you can have the overview of the process. I think it's very clearly demonstrating the flow chart coming from the 10 different solutions, which after extensive screening in the lab conditions, we selected 3 formulations which were the best performing. Then we ran the performance testing, having various of tests, and I will show you all of them. Then we selected the best formulation, which was then upscaled and used for the demonstration. We started from modification of radiata pine. That was the screening materials for us. That's the benchmark for the impregnation. But then the demonstration the upscaling process was done for radiata, for Scots pine, for European beech, and for maple. So we were able to demonstrate the technology on 4 different species. So coming from the first case, it was really exploratory phase. We received so many different samples, and here Lex will step in and will tell us how the screening phase was conducted.
Yes, thank you. Yeah, as Anna mentioned, we screened 10 different formulations, and on the right picture you see that we made several samples, quite small ones, some bigger ones for different types of testing. The smaller ones were mainly used for the durability testing and the larger ones for other purposes, such as weathering. The process itself is rather simple. We started with simple vacuum pressure impregnation. First, we apply a vacuum to suck the air out of the wood and make space for the impregnation solution. And then we apply a pressure of approximately 9 bars. And after that, we have a vacuum phase again to make sure that the samples do not leach that much anymore. After that, we cured the samples in an atmospheric oven at 130 degrees. Well, the table below shows the sample sizes. In total, in this phase, we did about 380. We made about 380 pieces and sent them to Inner Renew for further characterization. Well, the process itself, we didn't need to optimize a lot because the main goal was to reach an as high retention as possible. That's why we applied this full cell to refusal process. In general, when we optimize the impregnation process, we try to limit the uptake of impregnation fluid, but in this case, we really need a high retention to get enough performance. So that's about it.
Okay, so I will continue with the screening phase. So here you can see a lot of tests we were running on all of this radiata pine, which was treated with 10 different solutions, 10 different formulations, and that was like the big screening phase. And I was like, we received several hundred or maybe thousands of samples, and then we were like dividing them to the test. And this is like just the snapshot of the different tests we were doing. So you could see like there was like the leaching done, durability, hyperspectral imaging regarding where is the formulation is penetrating the wood. All of those tests were done, and after that we were and then of course we generated a lot of results, and after that we were like trying to identify what is working best and what is like the most suitable for our future application. So you could see like even the VOC emission, for example, even you can smell nice barbecue the smell from the wood. The VOC were able to prove that the VOC is not problematic. The thermal conductivity was done, and the sorption, desorption, shrinkage, swelling, all of these properties. And after that, we're able to identify our superhero treatment. So that was the treatment H, which was like the performing best in the most critical aspects. So for example, like we were of course considering the color, but for example, the fixation rate. So it means how much liquid is staying after the leaching was very important. For example, also the durability was very relevant for us, the shrinkage, swelling, and so on. So you could see like based on this screening phase, we're able to identify the best formulation, and also we're giving some recommendation what else could be as a plan B or C can be also used for the future upscaling. And then coming with that one, after the screening phase, we were coming to the performance testing. And this is something which is, you can still see some samples in the labs when we'll be visiting, and you can still see the stands because the test, we still have 1 month of the project to conclude. So some tests are still ongoing just to give the short, bigger span of the time. So here, I will give the word of Lex, because for this phase, the wood was treated in the higher amount in the pilot scale plant. So Lex, the word is yours.
Yep, the picture on the left shows our pilot plant. So you see, we just simply stack the wood and put it into the vessel. The process itself is more or less similar to what I've explained before. So simple vacuum pressure treatment. I think the next slide. Yeah, it shows like the graph on the right shows the second stage of the step. So the actual curing in a pilot plant. In this case, we can also in this stage we could also control the humidity. because you need you have like bigger sizes of board. We have to dry the moisture carefully out of the wood, otherwise you will get cracking. So you can see that in the first stage we are at after heating we are at constant temperature, and we slightly reduce the humidity to make sure that the moisture evaporates slowly out of the wood. We have to be at really dry levels before we can raise the temperature to about 100 degrees, and then we have like a steam drying process to about 110 degrees. And then we elevate the temperature 130 degrees for 24 hours, because we estimated that we noticed that we needed this curing temperature for to prevent leaching. And after this process, we also did some remoistening to make sure that the wood relaxes a bit. So that's about it for the curing process.
Okay, so yes, so this part was performed on 4 different species: radiata pine, European beech, Scots pine, and maple. So we have like here representative of the softwood and hardwood, so which is like in line with the current trends of the bioeconomy, also to use in the building sector, for example, wood which is not typically used as a beech, for example. And then here, sorry, this is also Lex, sorry, I step in.
Yeah, so the implementation results are shown here. The different wood species have different characteristics and also different uptakes. So you see that the average uptake of radiata pine is the highest, which is also according to expectation, and also at a level that's good enough for decent performance. The beech shows really high variability, which was also more or less expected. But what we did expect is that we had less variability in the Scots pine, and also we saw that it was just the penetration of the sapwood was not fully penetrated with the impregnation solutions. So that was something we wanted to work on. Next, please. Well, that's actually what I already told. One thing I didn't, that in order to increase the uptake on European wood species, for example, this pine, BTG also developed a low viscosity resin, and we're currently still impregnating with this solution to see if it improves the uptake.
Okay, so then after the wood was impregnated in the bigger scale, we received huge boards and which were shipped from Netherlands to us. When we will be visiting composites lab, they are still there, so you can experience them, but you can also see some of them which are implemented outside and also on this demo booths, so we're able to use them. But what was the next step? It was performance validation. So we had some screening phase, but then we wanted to make further tests just to identify like what is the really performance, and then if the application which we had in mind, which was mainly cladding for the wooden facades, is somehow feasible for this treatment. So we ran natural weathering, artificial weathering, durability test, fire test, mechanical testing, and cytotoxicity also to prove that the formulation are not toxic. And then we have the in-field testing just to see in-ground durability. And then what is also relevant, we were testing machinability and suitable mounting, because at the end we wanted to have these materials like the workable and also implemented in the demo building. So here we have our weathering stands. I think the weather will improve, so we will have sun as that. We had very foggy weather in the morning, but if somebody is interested after the meeting, we can go to one floor up, and when we see we have the weathering stands, we have this done on different configuration, on the vertical and 45-degree, exposed to the 4 cardinal directions. And here in Isola, we are like running this weathering trials from the beginning when the building was finished. And then the NewWave samples are exposed among other materials which we have the weathering, but you can see here this line, that brownish line over there. So those are the samples from the NewWave, which are benchmarked to the not weathered, not treated wood. And then here we are making regular photos, and then with always compensating with the color checker, and then later we will be able to see the change of the appearance. But of course, this weathering tests are long-lasting, and then everyone who is dealing with the materials knows then this is like typical for some locations, and then therefore as a benchmark is the artificial weathering is like recommended. So again, here we were like using artificial weathering machine, which is not fully simulating the real condition in service, because it's just like they're using the spray, the watering the samples and the UV radiation. Nevertheless, this is the standard, which is somehow allowing to compare at least the materials we were testing. And then here we were like, you can see the samples after weathering test outside of the room, and they are like exposed before and after weathering and treated and untreated. And here you can see the color changes. So what was the most important for us is like the after measuring the CLA B and gloss, we would like to see materials which are not really changing the appearance. So in our case, the pine seems to be much more stable for the artificial weathering than the beechwood. And then another test which is like really relevant for our application are the durability tests. So here the big thanks for our crew who was doing those tests. And then we were testing against Trametes versicolor and Rhodonia placenta. And again, during the first phase, we were already able to prove then the wood which was modified was achieving durability class 2, which was very good because that was one of our milestone. And here, once again, we were running the durability test. And then after the also improving of the curing and impregnation process against the white rot, we achieved durability class 1, which was the big surprise, and then like really nice step. With the brown rot, our test failed because didn't pass the results which was supposed to have like for the validity with the reference sample. So we are repeating some of them, and we have still them in progress. And then here you can see the results of the white rot with Scots pine, radiata pine, and European beech. So all of those were like achieving durability class 1, which is like really nice, and then is a significant improvement. We were also running those durability tests for other materials, but nevertheless we focus here on the wood modification. Then another important parameter for the wood in application when we think about the application in building, of course, we would like to have the buildings which are safe. So we also ran the fire test. So we did this with a collaboration with our with my past employees, CNR Ivalsa, and then we were assessing the beech and pine in the cone calorimeters. And of course, we generate a lot of data, but just summarizing. So here we were able to see that the beech was lower to ignite, and then so retains more mass. So was having a bit better fire behavior, and pine was like faster to ignite and then more flammable. And then the modification was like really neutral for the beech because it was like quite resistant. But in case of the pine wood, maybe some fire retardants might be considered when we just think about the future development. And then also mechanical testing. So it was like, of course, then when we have any modification of wood, and this is valid for the impregnations and also for the thermally modified wood, the wood is usually very much more brittle and less resistant for the impact bending. That was also our case, but nevertheless, for the application for the cladding, the mechanical strength is not really the relevant. So it was like reduced in general, but the treatment still we selected was not reducing that much the impact bending. And then also when we had the one of the phases of the project, we had the expertise here in-house. So we were trying to assess the cytotoxicity of this formulation because, of course, the performance aspect is important when we think about the new products, but we would like to have something which is safe for us, and then it will be like, not harmful for the humans. So our colleague was running such tests, and we were able to prove then the formulation which were developed in the project were not harmful for the humans, so which was nice achievement. Then we have the in-field testing. So this is sort of like it's called like graveyard testing. And here, because of the limitation of the duration of the project, we didn't do this with the standard diameters of the sticks, which are like half meter and bigger one. We did this with the mini sticks, which are like somehow accelerating this test and giving faster results. And those are still in progress. So you are welcome to see in the one of the sites of the building and how they look like. But in general, you are like measuring the sample, the weight of the samples before and after the test, and you are just calculating the mass loss. You can also see the appearance of the surface, integrity of the materials. And this is especially relevant in the conditions when we have the termites and so on. And here we don't, so it's just the attack of the fungi which are in the soil. And then what was also important was the machinability, and because somehow after the performance testing, this is the wood should be like able to be applied in the real construction. So we tested machinability for different products in the NewWave, not only modified wood. So here you can see, and then we were able to give some recommendation, but in general for the modified wood. As any other modification process, we experienced the materials was much more brittle, and then so perhaps it's also worth to consider when we will be having like these materials on the as a cladding on the facades. Perhaps some pre-drilling is recommended just to have the better fixation, but regarding the mounting process, whatever is applied now for thermally modified wood can be directly implemented. The same system can be implemented. So that is also fine. And then here, when we were preparing the demonstrators, and you are welcome to see some small mock-ups outside and also the real mock-up in front of the building, we were playing a bit with different materials we receive. So we had 4 different wood species, and we were also playing a bit with different configuration, trying to make this like horizontal, vertical with some spacing between them, so you could see how they look like. Okay, and so now we are at the end of this workflow from the beginning, coming from the screening phase to performance testing and demonstration. And we develop 4 different configurations for implementation of the NewWave, all the products, not only modified wood, but you could see here with the colors, they are like materials which were generated and produced in the frame of the NewWave project, and how they were implemented in different configurations. So our architect was making the design of the walls, and they were like then in parallel the beam design was developed to optimize the parameters and just to see like so the facades are stimulating the real facades which are in the use. So they have some parameters which are like fine with the building physics principles. So this is the mock-up of the wall 1. Of the wall 2, so some of them they look a bit similar, but they have different materials inside. The wall 3, and then wall 4. And I think the demonstrator outside can tell you much more. You can touch the materials, you can smell the materials, experience the materials. So welcome to do so. And then the demo site looks like that. I hope the fog is going down, so we'll be able to see this. You are able to touch the materials and to see how they look like. And the NewWave's materials are on these 4 squares, and then everything is cladded with the Foreco cladding, the same cladding as we had on our building. If you will just look from the window, you will see a bit of grayish color. This is like how it looks like when it's just after the treatment, so it's brand new. And then we expect some weathering also to be done, but we'll be able to compare the performance of the NewWave, also considering the benchmark product, which was produced by our partner. So with that, I'm concluding. I think we are good with the time. So yes, so I think questions will be done later, and then just announcement for people who are here. We will go now for the coffee break, but we would like to take one more photo with you because we have different configuration of partners today, and we have also people from outside for this conference. So we would like to have the final photo and then to invite you for the coffee break.
Just Just for the people connected online, don't forget to post your questions in the chat that will be answered later in the Q&A part. We will resume the event at 10:30. Okay, we are back here, and the next part we'll see our partners IP Polymers and TFC talking about innovative green chemicals. So I give the floor to David from IP Polymers.
Good morning, everyone. My name is David Kontus. I represent my company AP Polymers, and I will give you a short presentation on how we utilize some of the innovative green chemicals produced in the project to develop some polyurethane products. I'm gonna just introduce briefly our company and what we do and what our expertise is, and then I'm going to show you some of the examples of the activities that we perform within the NewWave project. So AP is a private-owned company which was founded in 2013 and is situated in Area Science Park in Basovica in Trieste, which is one of the biggest technological scientific parks in this region. And we are focused mainly on industrial R&D, where we develop novel bio-based chemical building blocks and formulations for application in the following sectors. So basically, all of the polyurethane spectrum is covered, and also composites and and from recently also thermoplastics. We have a sound knowledge in organic chemistry and polymeric science, and we use it to develop new bio-based polymers and validate them against commercial benchmarks, but also test the usability of novel bio-based products, such as, for example, cashew nut shell liquid, lignin and lignin derivatives, plant-derived oils. We do not have any commercial or production capacity. Our knowledge and our recipes are our products, basically. So we usually operate on a technology readiness level scale, which goes from 4 to 5. So we are in the middle of the TRL scale, let's say. And this offers us the opportunity to work both from a scale up and a scale down perspective, and gives us also the possibility to produce samples, prototypes to our customers, which are representative of specific applications. And our revenue streams mainly consist of short and medium-term consulting projects, but also of master service agreements, which are broader development work agreements with long-term commitment and priority in the R&D time. But throughout the years, we have also participated in many funded research and development projects, mainly from the EU programs. And these have been a great opportunity to also work with new materials, gain new expertise, and broaden our network and meet new partners. So this table summarizes all of the European projects that we've participated in from our conception, basically. And they are categorized based on the type of material that was employed in each project. And most of these are now completed. NewWave will be completed in 1 month. And the last ones remaining are Airlight Biocom and Aeolian, where vitrimer resins are being developed on a bio base. So moving on to NewWave, we were in charge of leading the manufacturing line 1, which is the manufacturing line for the production of polyols and polyurethanes, where the FPBO-derived pyrolytic sugars have been fractionized to obtain polyols, either higher molecular weight, but also lower molecular weight polyols obtained by further purification of the polyol fraction. And we employed these to produce novel bio-based foams and adhesives, which were utilized in the production of CLT and composite polyurethane wood panels for the construction industry. But we also had the opportunity to work with other innovative chemicals, which are derived from foreign derivatives and come from the manufacturing line 2, which will be explained in more detail by Rick and the project partner Transfuram Chemicals, which were in charge of leading this manufacturing line. So as you can see, here we are working with glycols, and they represent an important building block in polyurethanes. And the ability to use bio-based glycols means that we can impact the sustainability not only of the raw materials for the production of polyurethanes, but also of the final articles. When we talk about polyurethanes, we can either refer to the synthesis or to the formulation. And in this case, AP was in charge of both the synthetic and the formulation aspect within the project. So we utilize these innovative bioglycols as raw materials for the production of polyols, such as polyesters, polycarbonates, and polyethers, which are then employed in the formulation of polyurethane articles like foams and adhesives. And while synthesis and formulation are the major aspects, we have also to make sure that the materials we are working with meet certain criteria for this application. So everything starts with characterizing these bioglycols and making sure they are suitable for this application. And if they are not, then we need to modify them. And the approaches can vary based on the type of property that needs correction, basically. And only then can we move on to the synthesis and to the formulation. Once we have the formulated product, we then test it and benchmark it against the reference products. And based on the test results, we can either move back and modify the formulation, the polyol, or further modify the glycols in order to meet the target benchmark that we are looking for. Some of the synthetic pathways that we have explored within the NewWave project, starting from some of these glycols, include the synthesis of polyester diols, the synthesis of polycarbonate diols, and the synthesis of polyethers obtained through basically ring opening of epoxidized precursors. So you can see some of the applications in which these diols can be utilized and in which they have been tested. And for example, in these two pictures, you can see some of the tensile specimens obtained with polyesters and polycarbonates based on BHM-THF, which is this molecule here. And while we did not obtain great results with it, it still has a lot of potential for further research. And the ones that we mainly employed in the final products were based on these two glycols. And basically, the polyols that were obtained from the ring opening of epoxidized precursors were then utilized to formulate polyurethane adhesives. So I'm just going to summarize quickly some of the results that we obtained related to the polyurethane adhesives. So we managed to develop several polyols based on the bioglycols derived from pyrolytic sugars with a bioglycol content of up to 32%. Which was one of the targets, let's say, also of our work. And we then employed these glycols as these polyols as the sole components in the polyol part of the adhesive formulation. And we managed to obtain two systems that meet the criteria for D1 and D2 durability class requirements according to the specified standard. Here you can see a summary of some of the systems that were developed. As you can see, this is the threshold for the D1 durability class, and these two polyols clearly surpass the threshold. And the same two polyols also are eligible to be considered D2 durability class type of adhesives, as they also managed to pass the required threshold for this durability class. And moving on to our second targeted article, which are the composite plywood polyurethane panels. We developed these by utilizing the plywood panels produced by Foresa, which were explained in detail in the previous presentation, and combining them with our bio-based foam that we developed using a heavy polyol fraction of the first pyrolysis bio oil. We obtained this composite, sustainable composite polyurethane plywood panels. The key results are summarized in this slide. So we managed to replace part of the reference petrol-based polyol with this bio-based polyol derived from pyrolytic sugars. And by optimizing the reaction parameters to meet the requirements for the production of this type of panels, and obtaining a foam with properties comparable to the reference. The foam was then utilized to produce 15 panels in total, 8 of which were used for the assembly of the mock-up that Anna showed in her presentation, and they covered a total surface of 2 meters square. And these panels have comparable properties in terms of mechanical, thermal, and acoustic performance, comparable to the reference panels obtained with only the petrol-based foam and the plywood panels. While we did manage to get some results, initially we met some major hurdles in the initial stages of the work, such as the purity and the complex composition of the biomass-derived raw materials meant that we usually had to adapt further purification steps to meet the quality standards to use them in the polyurethane applications. And initially, they also had a residual smell, which was quite noticeable, but in collaboration with BTG, we managed to reduce that. And especially with regards to the foams, the smell is basically gone now. And to end on a positive note, what we did manage to achieve is the successful integration of 3 different bio-based building blocks in the targeted end products, and also obtaining composite panels with a performance that is comparable to the reference without compromising the cost. And that's all from my side. Thank you for your attention. I'm leaving the floor to Rick.
Okay. Morning, everyone. So I'll talk a little bit about next like this. So my name's Rick de Klerk, and I'll talk a little bit about furanic derivatives as innovative green chemicals. So I'm from the company Transference Chemicals, or TFC in short. For those who don't know us, I'll give a small company introduction. So we are a bio-based chemical manufacturer. We are located in Belgium, in the northern part of Flanders, more specifically in close to Geel. We've been active since 1972, so a little more than 50 years by now. And we have a total production capacity of more than 40,000 metric tons a year of bio-based chemicals. In total, we are about 50 full-time equivalents working. That's distributed between our production site in Belgium and also our sales office of IFC in the Netherlands, which handle most of our sales of our products. We are ISO certified for quality and environmental management, and we have an EcoVadis Gold label. And this is just an aerial picture of our site, just to give you an impression. So what is our core business? It's actually within the furfural-based chemistry. In a nutshell, we turn agricultural crop waste into bio-based chemicals and polymers. Our main activity is the production of furfuryl alcohol from furfural, which is our raw material. And we've been doing this for 50 years and produce more than approximately on an annual basis about 36,000 tons of furfuryl alcohol, making us one of the largest producers in the world. And more recently, we've also expanded our product portfolio into tetrahydrofurfuryl alcohol and also 2-methyl tetrahydrofuran. And these are all derivatives of all related to the furfuryl alcohol production. As you can see, all of these reactions consume hydrogen. So that's also where our expertise is. We have access to hydrogen through pipeline, and we are specialized in hydrogenation of furanic derivatives. We are not a producer of furfural ourselves. That is mainly done by our mother company, the Central Romana Corporation in Dominican Republic, although we also source furfural from other places in the world. But in essence, it's always derived from hemicellulose, which is in turn derived from the bagasse or the plant residue from sugar production. So our main source of furfural from the Dominican Republic is coming from sugarcane production. So basically, after getting the sugar out of the plants, the bagasse that remains, the stems, the leaves, they are treated with acid and steam, forming furfural, which is then purified, distilled, and shipped to us as a raw material. But since all of our products are coming from the hemicellulose, basically all of the carbon in our products is derived is bio-based. And in total, more than 97% of our raw materials is bio-based and by preference made from agricultural waste streams. Right now, only the hydrogen is not bio-based, although we are also working on projects to getting hydrogen from green sources and making it also renewable. Aside from the hydrogenation activities, we're also producing some polyfurfuryl alcohol resins. This is always done in close collaboration with customers, depending on the applications or properties they want. We specifically tailor and develop PFA resin systems and formulations with our customers. And I think we have a capacity of about 2,000 tons a year of these PFA resins. So where will you find our products? The main application for furfural and furfuryl alcohol is in the heavy industry, so foundry and refractory. So you're making these big sand molds for casting molten metal. Let's say if you like these big engine blocks or windmill parts, the sand molds are mainly based on furfuryl alcohol-based systems. Then also you have the building and construction. That's mainly for the PFA resin, so insulation, high-pressure laminates, and modified wood. And then also there's a composite market, so fire-resistant composites, biocomposites, or NFRP, natural fiber reinforced plastic composites. Those applications are mainly in aerospace, rail, public transport, and automotive. And then finally, there's also a pharma, cosmetics, and fragrances market. This is mainly for the methyl THF and the tetrahydrofurfuryl alcohol. Methyl THF has a large application as a solvent in API production in the pharmaceutical industry, and also used as raw material, and also for cosmetic ingredients and fragrances, and also agrochemicals. Yeah, we have a wide variety of lab reactors, but I will just skip this. So let's talk a little bit about our activities in NewWave project. So just to give an overview, where in the project we are located, we are in manufacturing line 2. And for us, the project, our goal was actually to do chemical upgrading of HMF and other furan derivatives through hydrogenation and hydrogenolysis. So looking at how the project is outlined, it starts with the FPBO samples, the pyrolytic sugar samples produced by BTG. Those were sent to the University of Groningen to do analysis, optimization, and to a lab scale production of HMF. That information was transferred to FHNW, who were responsible to do the upscaling to bench scale HMF production. And then finally, our goal was to upgrade this HMF and other furan derivatives through hydrogenation. So talking about the furanic derivatives, this pool here are the molecules that I'm mostly talking about. So we have the furfuryl alcohol, methyl furan, but then in extension within the NewWave, also the 5-HMF and the BHMF. And as I've said, we are specialized in hydrogenation, this is our preferred route to do valorization of these products to get these fully saturated components right here. Although we're also interested in a defunctionalization, although these reactions also require hydrogen, you could produce methyl furan or dimethyl furan, which could be interesting on their own, but they could also serve as a raw material to do a second hydrogenation to basically get the same products, but then in 2 steps. So within the NewWave project, we started with the hydrogenation of methyl furan to methyl THF and also furfuryl alcohol to tetrahydrofurfuryl alcohol. We use these 2 molecules as a sort of case study. It's a little bit easier to do. Also, these 2 products have an existing but growing markets. They're already being used in industry right now, and we have access to these molecules, so it makes sense to do these conversions. And the idea was to optimize these processes. At TFC, we already developed a process to do dehydrogenation, but within the NewWave project, we were able to optimize these. And the idea was to use the knowledge that we have for these conversions, the process conditions and the catalyst development that we did, and then subsequently apply it for the 5-HMF hydrogenation to get this new molecule right here called BHM THF. This molecule right here is not currently commercially available, So it's basically kind of a new product, but since it's a bio-based diol, it could have a lot of potential applications in, for instance, in the polymer industry, polyesters, polyacrylates, polyurethanes, but also maybe as a solvent on its own. So this is really an opportunity for new application and markets. So what we did in the NewWave project is we at TFC, we developed a hydrogenation process to convert methylfuran to methyl THF and furfuryl alcohol to THFA. That was a process that was already developed before, but within the NewWave project, we were able to optimize it to continue our R&D with the scope of actually scaling up this technology. And in the end, we managed to get a final process with and developed a catalyst, which was really selective. We do this conversion with more than 99% selectivity. And also because it's a quite exothermic reaction, a double hydrogenation, you also need to have a good process control and think about the safety when you're scaling up. And basically within the project, the last 4 years, we have developed a commercial plant, which started up Q1 of last year. And we have an annual production capacity of more than 4,000 tons per year. So basically we went from a TRL 4 to 9 within the NewWave project. We basically skipped the pilot plant scale, so it was a little bit risky, but everything turned out really well, and now we have a full plant in operation. And the picture on the right here is just a picture of the crude product coming out of the plant from our first batch after going into operation. So right now we're working on the commercialization of this 2-methyl THF. So it's a new bio-based solvent. And right now we're the only producer in Europe for this product. There are some suppliers in China and the US, but not right now we're the only producer in Europe. This is just an extract from the sales data sheet from IFC, our sister company. So you see the specification, the sales specification in terms of purity, it's 99.9. That is because it's mainly used in the pharmaceutical industry. They require a really high purity. So I've already talked about this application. So this is now commercially available for us. So if you're interested in any samples, please reach out. The tetrahydrofurfuryl alcohol is the same. The plant we built is able to produce both products since it's a very similar process. Here, the specification is 99.0. That's because it's not really used in the pharmaceutical industry. This solvent is mainly used as a cleaning solvent in electronics. That's a big one, but also as a synthetic intermediate in the formulation of agrochemicals and so on. So here the purity is a little bit, the purity requirements are a little bit lower for this product. But this is now also commercially available here in Europe. So then we moved on to 5-HMF and tried to convert it to BHM THF using the same technology that we developed for methyl THF and THFA. So we got some 5-HMF from our project partners in 3 different grades. We tried to convert these different grades. There were some differences, but in a nutshell, we compared the hydrogenation of 5-HMF using a conventional hydrogenation process, and then compared it to the TFC developed process just to see if it would perform better. And you see that if you just use a conventional hydrogenation process, the selectivity is only about 80%, whereas if we do it in our optimized process, we get a selectivity of about 95%, which is quite a significant increase. So that's good, although there are also some challenges with converting 5-HMF. That is mainly related to the catalyst lifetime. We see it's much more limited compared to methyl THF production because of impurities in the HMF source. And also 5-HMF has an extra aldehyde group, which methylfuran, for example, doesn't have. And to hydrogenate an aldehyde group, we typically need other active catalyst sites than you would need for an aromatic ring hydrogenation. So in a sense, there is some catalyst development required. We could not use the same catalyst that we have for methyl THF. And then a third challenge is the formation of solid byproducts. But this is mainly related to if you have a low selectivity, you could form some byproducts which precipitate and then they cover the surface of your catalyst and then just dies immediately. So that's all related. Now, what we did in the NewWave project, so we also did some catalyst development and process optimization. This figure on the right here just just demonstrates that if we use the standard catalyst, even in the first run, we're not able to achieve full conversion. That's just because the catalyst deactivates way too fast. But we developed a promoted catalyst, which is much more tolerant to the HMF impurities. And it also has an improved activity towards these aldehyde groups. And in this case, for instance, we were able to get a full conversion for one run. And in the end, at the end of the project right now, we have developed a catalyst which is able to do multiple cycles of dehydrogenation. So we have a strong improved lifetime while also maintaining a high selectivity. So in the first run, we have about 95%. It drops to 90% over time, but it's still quite high compared to the standard catalyst, which after run 1 is already deactivated. So that's basically a strategy, but the catalyst development definitely needs further improvement as well, and it's still ongoing. So we also looked at the purification of this BHM-THF. So we did a vacuum distillation and we were able to produce more than 0.5 kilogram of sample with a 98% purity. That sample was sent to AP for some preliminary testing. And only a limited amount of tests were done, as David mentioned, because it was not within the scope of the project, but still we wanted to do some tests to see if it had potential. The polyurethanes that were made did not show any improved performance yet. But as I said, only a limited amount of tests were done. Maybe the purity of 98 was not enough. But nevertheless, it's still a very interesting molecule. And we've produced more of it. So currently, we have about 1 kilogram of purified BHM-THF samples available at TFC. If anyone is interested, please reach out. We have it available to send out to people that are interested in testing it. So the 98% pure BHM-THF, it's a clear to slightly yellowish liquid. It's pretty viscous. It has a viscosity of about 200 centipas and a density of 1.15 grams per milliliter. And also the color is quite stable. It doesn't change in color over time. So this is available for anyone interested. And then on final note, we also worked on the defunctionalization or hydrogenolysis of furan derivatives. So we started with the furfural conversion to methylfuran. This is a process that is already applied on industry. We're not doing it ourselves, but it is already commercially available. But the catalyst used is usually the copper chromide catalyst. That's the industry standard, which is quite toxic. So within the NewWave project, we also developed a chromium-free but bimetallic catalyst, and then also screen and optimize the reaction conditions. And the best results we achieved were a selectivity up to 80% of methylfuran. Now that is not including furfuryl alcohol, because one of the byproducts is furfuryl alcohol. But for us, as being a furfuryl alcohol producer, it's not really a byproduct. So if we include this product in the selectivity calculation, we basically get a selectivity of 95% to interesting products for us. Challenges and improvements. I think the main challenge here in this process is the product recovery. If you form methylfuran from furfural, you release water. You can't go around that. So you need to separate this product from the water. It's insoluble in water, so you always get two phases that you need to separate. And then second is also the condensation of methylfuran. Methylfuran is a really volatile molecule. It only has a boiling point of 60 degrees or so. And this process is usually done at low pressure. So it's not that easy to really condense the methylfuran from the vapor phase, especially if you dilute it in hydrogen. So that's a challenge. And then also the catalyst lifetime. Right now, I'm not sure if it's sufficient for industrial process. We were not able yet to do actual runs of multiple weeks. Although we have seen that the catalyst does go on for quite a bit, but it needs more testing to actually validate whether in an industrial environment it would last several weeks. And in addition to that, we would need to look at the regeneration of the catalyst. If it deactivates, that's one thing. If you can regenerate, that's another. So that would also need some more work. Now, regarding the defunctionalization of 5-HMF to DMF, unfortunately, this process for methylfuran is not applicable for HMF, and that is because HMF it's a solid crystalline. It's a solid. It's not volatile, and it's actually too reactive to vaporize it. So I'm doubtful that this process can be translated. So just as a proof of concept, what we did is we used the same catalyst used for methylphenol production, so a catalyst able to do this reaction, but then basically use the liquid phase process that we developed for methyl THF and combine them. And without any optimization, we were able to achieve a 90% conversion and get a 30% DMF production. So yes, in a sense, this reaction can be done, but still we had approximately 40% intermediates and 10% residual HMF. So it's by far fully optimized. So likely for this process, you will need an entire different process than methylphenol production. So just to summarize our activities in the NewWave project. So right now, the hydrogenated furanic derivatives available, we have methyl THF and THFA. Both are currently at a TRL 9. So commercial unit is running right now. For the BHM THF, I think we're around TRL 3 to 4. We have done proof of concept and also validated in the lab. Although I'm not sure if it's already ready to go to TRL 5 in a pilot scale environment. It probably needs some more work to improve the catalyst and lifetime and find a catalyst that's even more tolerant to the HMF impurities. For methylphenol production, we are at TRL 4-5. So we have some basic results already. Product recovery and lifetime needs improvement, but we are still moving forwards with this, and we'll try this reaction also in the pilot plant that we have at TFC, which would then be TRL 5. And then finally, the DMF production from 5-HMF, currently it's just a proof of concept. I think it's just in TRL 2 at the moment. This would need a lot more process and catalyst development to actually look into this reaction. So thank you for your attention.
Okay, thank you to our speakers. So we are almost on time and it's time for the questions. Actually, we received already some, and there is one for Lex from Foreco. I don't know if he connected or not.
He's connected. He answered online, but maybe he can also answer loud, so we all hear. And
okay.
So you can read the question, and then Lex will answer again.
Fantastic. So as a commercial timber company, and given your experience with the NewWave project, what would be the most important next steps to successfully develop a viable bio-based product in the market? And which markets are you targeting? So Lex?
Yeah, in the NewWave product, we mainly focused on cladding applications. I personally feel that the traditional creosote markets are more suitable for the product because of the look and feel of it, and also that we can achieve rather high durability classes. Yeah, in the Netherlands, the main market for or the traditional markets in the creosote are mainly creosote poles, so telephone poles and railway sleepers. That's not a typical Dutch market, so it's not. We are mainly focusing on the Dutch market, so it's not something we want to do. But I think to overcome the most important market barrier, you need a manufacturer that is active in those types of markets, because we have quite a lot of work to do regarding to all the types of regulations we have to fulfill if we want to actually enter the market. I hope that answers the question.
Okay, thank you. There is another question regarding the comparability of the results to standard materials and methods. Did you benchmark your approach against conventional technologies, either at the process level or for the specific steps such as pyrolysis, panel production, impregnation, or green chemical production in terms of material balance and energy demand? And if so, are these comparisons published anywhere? Regarding this last part, yeah, there are already some result summaries published on the website. perhaps the colleagues working on the modification of wood could answer, because it's not directed to anybody specifically.
I think this is general question for the coordinator or for the partner from the environmental assessment, because it's general for all manufacturing line.
Mm-hmm.
Yeah, and we're also a lot of questions in one. I think within the project, and probably indeed Blue Synergy can answer also that question. There is an integrated approach looking at all the different steps. For pyrolysis itself, the starting point, it's already quite clear because it is commercial and implemented, and from there on, of course, we make all the mass and energy balances and do the individual evaluation of each manufacturing line, and of course also in the end you have to compare it to the alternatives and whether it is competitive. In the whole approach, also from the fractionation point of view, it's the concept is also that you can take out one component and the rest is still a fuel. And at the moment, all process oil, or most of process oil, can be used as a renewable fuel. And that's still the case. The only thing what we are doing, we take out a little bit of a certain product, for instance, the lignin or the sugar, and go in that manufacturing line. So within the project, we did a completely integrated approach, assume everything is used. From a commercial point of view, it might go step by step and take out one new bio-based product at a time. It's okay. So Blue Synergy has nothing to add?
This is Sebastian from Blue Synergy. I think that aside from this, the only one thing that can be added is that we are doing this assessment based in a mass allocation. So we are sure that all in the, let's say, this biorefinery concept is accounted in a way that it doesn't double count in terms either of economy or environmental impacts. So we try to keep all the mass and energy balances well accounted across all the manufacturing lines. But aside from that, yes, I think Bert already answered it perfectly.
Okay, thank you. Are there any questions from the audience here present? There's a raised hand.
Okay. Elena Conti, Catas, Italy. I have a question about what can be the economical impact of using green chemicals as compared to traditional chemicals in bio-based products.
Okay.
I think the first step, like the first economic impact that you notice, is that the cost of production will rise. Maybe by a little, maybe some more, depending on what are you replacing. But also at the same time, you will be going for a different kind of customer, one that is looking for a more premium, more eco-labeled product, and also the options for the market for your product will be, let's say, better. So you normally will see that this rise in the production costs will be compensated by the amount of sales you could obtain from a better positioned product. And I think that also in the future, this increase in cost of production will be lower and lower until at some point it will be even better than the original production cost.
Maybe just to add something, with chemicals you're replacing something different which has normally a higher value than energy. What we do at the moment with process oil, it's mainly energy. But then it depends on what you replace, and not always exactly the same chemical. For instance, the lignin replaces phenol. So you compare, in fact, the lignin price to phenol. Phenol has a quite high price. And I guess with the development of the oil price in the last few days, it's going up at the moment. But you replace something with a much higher value. So then you only replace a kind of functionality, and it's not exactly the same chemical. For furfural, I guess it's completely different because that's already bio-based. And so it's not really transferring to something green because it's already green. But there's mainly now looking at other functionalities or making new products, etc. So it can be very broad. What we always see is that chemicals very often have a higher price, but to produce them, it's also more costly and needs more steps. And in particular, I think one of the key things is also on purification and recovery, etc. But
yeah, one is enough. Thank you. So yes, about the economic impact of bio-based chemicals, either you have a replacement chemicals, which have also a fossil-based alternative, let's say. But for our case, for instance, in methyl THF, it's a product that you cannot obtain through fossil-based resources. It's already coming from furfural, it's already bio-based, but it also leads to new markets, which can only be obtained through these bio-based chemicals. You cannot, I mean, for instance, the alternative, fossil-based alternative for methyl THF would be THF, I would assume, but it has totally different properties than methyl THF. For instance, THF is soluble with water, methyl THF isn't, so you would be able to do better solvent recovery and so on. So that's also another side of the economic impact of bio-based chemicals, that you can really apply new markets and new applications which would otherwise not be attainable with fossil-based chemistry. So
necessarily has to be a negative impact. It can be also a positive impact. In fact, that was the question.
There's a raised hand there.
Hello. So I'm an architect, so maybe I don't understand chemistry so well, all the formulas, but please maybe to explain a little bit more that for me. So as I understood, the glues used in CLT products, for instance, they are bio-based, but not fully bio-based, or still. Is it still going to be a little bit toxic? That's what my question. If I explained well.
Yeah. So basically, these adhesives that we developed are two-component adhesives. So one part is the polyol that we developed, which is partially bio-based, and the majority of the formulation, as with all of the polyurethane products almost, is made from isocyanates. So those are so far intrinsically petrol-based. So that part and the toxicity associated with the isocyanate remains, but depending on the type of isocyanate that you utilize, the toxicity can be reduced. But unfortunately, yes, this is somewhat of a limitation of these products. And even if it were monocomponent adhesives like the industry usually utilizes, they are still based on isocyanates. So so far, these products remain at least partially petrol-based. Yeah.
Okay. Perhaps there was a question also for David that's linked to this. So you said that you have achieved the composite panels with performance comparable to fossil-based reference without compromising the cost. So can you elaborate on that?
Yeah. So when we used this polyol as a replacement for the standard petrol-based polyol, the formulation did not require any further modification. So basically, it was a drop-in replacement, let's say. So we didn't have to use any additional additives or catalysts in the formulation that could impact the cost of the production of the foam. So while it is only a partial replacement, let's say the cost will be related to the production cost of the polyol, basically. But no other modification was needed to successfully incorporate it in the formulation and obtain the properties that we were looking for.
Okay, thank you.
Thank you.
Are there any other questions here in presence? Okay, there was one question perhaps for Bert with respect to thermochemical fractionation. Do you see an impact of the original biomass on the fractionation process and the fractionation obtained? Do you observe a difference in lignin yield for different types of biomass? Okay, Hans.
Yep, thank you. So in general, what you see is if you use a different biomass, of course, let's say the ratio of hemicellulose, cellulose, and lignin in this biomass, it's different there when you compare the different biomasses. For example, woody biomass compared with straw or something like that, you have a difference in ratio of these main components, and you will also see them back in the pyrolysis oil. So also in the yield of the fractions obtained in the TCF. Yes.
Okay.
Yeah, the quality is we don't really see a difference in the quality. So let's say a lignin produced from straw or from grasses or from woody residues, for example, they can all be used in these applications in general. Yeah.
And maybe the origin of this biomass, you said straw, you said woody residues. How's the collection takes place in your experience? Because I imagine that in a scale up of this value chain, we could have the collection of these residues could be an issue.
Generally, you want to place the fast process. You want to place it where the biomass is available, so that the pyrolysis plant, and you want to connect your fractionation plant to this pyrolysis plant. You want to place it where the biomass is available. Yeah, that's what you want to do.
Okay.
Yeah, maybe one thing to add, and what we do is it's not a miracle, and I think it was on one slide where we let's say a general composition of biomass is hemicellulose, cellulose, lignin, and if there's limited lignin in the biomass feedstock, we will have limited pyrolytic lignin.
Okay.
And but I think for a lot of different types of biomass, the difference in cellulose, hemicellulose, lignin is not that extreme. And basically from all the biomass, you will get these products. I think we are less if we have, for instance, a lignin source and pyrolyze that and then make the pyrolytic lignin, that's not an approach we are really fond of. But so in fact, also the pyrolysis itself, it reflects the original biomass. It is depolymerized, but you will still, in that sense, recognize almost the original biomass. And after fractionation, it's the same.
Yeah, David.
I just wanted to mention, that there are bio-based isocyanates as well, but they are very costly. So industrially, they are not really utilized. And there are also approaches which try to not use isocyanate. So different approaches to the production of polyurethanes without the utilization of isocyanates. But these are only at the research level. And they are called NIPUs, non-isocyanate polyurethanes. However, they have high limitations in terms of reactivity, which makes them currently not utilizable industrially. But if you want to find out more about these products, you can search and you will find many reviews on non-isocyanate polyurethanes. So yeah. They are being investigated, but as far as I know, I don't think there are any commercial products at this stage.
Okay. there was another question for our host, Anna. Considering the manufacturing line for wood modification, which step of the project was the most challenging and which one the most rewarding?
Okay, I will comment this from our perspective, but maybe Lex would like to comment on his one because it was more practical. So I think like the most challenging was the moment when we received all of the samples for the screening test, because there were so many of them. There were like 10 different radiata pine impregnated with 10 different formulations. And that was like, you know, and then we have to plan strategically how to conduct all of these 15 tests to be able to select. So we had a bit of pressure, you know, how to optimize the testing. And so that was like the tough moment. But then we see the light in the tunnel when we arrive to our superhero. So when we were able to select the most performing, and I think the rewarding part was when we saw the materials which were upscaled and we were able to implement them in the demo building. So then it means then we arrived to the goal. So our first milestone in the which was related to us was achieve the durability class 2, and we were able to achieve that. And the last milestone in our what we were responsible for, we were in charge to prepare the demo building, and that was integration of all of these materials to show then it is possible, then they are integrated in the building structure. So this is from my part, but maybe Lex would like to add something, which was the challenges for the Foreco.
No, not really. I think you explained it well. The main challenge of this kinds of thing is always that it takes like a really long time, especially to do that biological durability testing. And yeah, that's always challenging because you have to wait for the results to continue. But I think Anna explained it quite well, so nothing to add.
Good. So perhaps we have time for one last question from here, or if there is another one online that I might have missed.
You showed this picture that it looks like the catalyst became better and better with time on stream, or the conversion went up to almost 100%, but it starts as a low value. What's the explanation for that? Or did I misunderstood the graph? That also possible.
No, yeah. In the beginning, you had a jump in the graph. That's just because the way we do the experiments. So that's because we monitor the hydrogen uptake. So in the beginning, the pressure needs to drop a little bit in the reactor before you actually supply pressure. That explained like the jump in the graph you had. And then the increased activity, it's actually something we see more often. It could be the catalyst we use. It's a pre-reduced catalyst that is supplied to us like that. But it could be that it's already active. So you have two kinds of catalysts, basically. You have one that are pre-reduced. They're already active when you add them. And then you have the stabilized catalysts. They're also pre-reduced, but stabilized. They will need some activation inside the reactor. The one we use, it's a pre-reduced catalyst, so it should be already active, which it is. But sometimes during the first cycles, we see an increase in activity. And that could be that it's a nickel-based catalyst, that these nickel sites, or some of them, they reactivate during the process because of the high temperatures and high pressures. And they form more active sites, which could lead to improved activity. But it only happens like the first run or the first few runs. In the end, we always see you always get some catalyst deactivation over time. But it is a phenomenon we have observed also in the commercial plant, for instance. We're not sure 100% why it is the case, but we do think it's related to maybe reactivation of some passivated sites. I mean, the catalyst has been transported and has been standing for a while, not under hydrogen. The catalyst really wants hydrogen. So when you start to use it in a hydrogen atmosphere, sometimes we see an increase in activity for the first hours or so. But I can't 100% explain why it is the case, just that it is a phenomenon we see from time to time. It is in the right direction, yeah. So we're not complaining.
Good. I think came to a conclusion, and I remind you that now we have the chance to see the mock-up structure outside, And thank you for your presence. Thank you for the participation to our online participants. And as I mentioned before, on the NewWave website, there is already a lot of materials for you to download, and more will come in the final months and weeks of the project. Thank you very much, and enjoy the rest of the day.
Yes, just one word, because some of participants were asking if the presentations or recording can be shared, and yesterday we were agreeing then yes, it can be. We will just decide jointly like what to do in the most like the optimized way. So we will decide if the materials will be online on the NewWave website, or we will be sending the information to the people who register, but we will be in touch. So yes, we will be sharing and dissemination the materials.
Yeah. Thank you very much.